So if I can get this factored and solved, I can figure out what's going on. So I look at this and say, all right, well, it's going to be x and x because that multiplies to the x squared, the first term. And then this negative over here means that I'm looking for, one of them's positive, the other one's negative. So one of these is positive, the other one is negative. And then I'm looking for two numbers that multiply to -3 that add to +2. Since it's positive here, that means the larger number will be positive. Smaller number is negative. Since do 3 and 1 multiply to 3, well, -3, yes. +3 and -1 multiply, do +3 and 1 multiply, or add to +2? Yes, they do. So then I've done it shorthand, but I'll just do it quickly here. I want to see, where does x plus 3 equal 0? And where does x minus 1 equal 0? Because again, if this equals 0, then 0 times anything over here is 0. If this whole parenthesis is 0, then 0 times whatever this is also 0. X plus 3, subtract 3 from both sides, x equals -3. On this side, add 1 to both sides, x equals 1. I have two solutions, -3 and 1. And again, if I were graphing this, which I'm not, but if I were, what I'm actually finding is that on the x at +1 and at 1, 2, 3, -3, it crosses the x-axis. These are what are called zeros. X plus 3 is a root. X minus 1 is a root. Roots and zeros are very similar to each other. But if I was doing a parabola, then I would know that the distance from -3 to +1 is 4, which means halfway is at -2. So somewhere on this, or -1, I'm sorry. So somewhere on this line, x equals -1, I write it as a dashed. The vertex will be on that. As a parabola, the vertex is the lowest point or the highest point. And this right here is positive. It's a positive number, which means it's going to open up. So we're going to get to a place here pretty soon where we're going to find that number and be able to actually, I didn't do a good drawing, but that vertex right there is on the line. So the vertex will have a point -1 comma something. And the way I would find it is I'd plug it into this equation to find out what that value is for where the vertex is. But we're going to actually figure out pretty soon how to factor this in such a way that we'll put it in vertex form. So fun stuff coming. So here we're going to go and just quick refresher on simplifying. You've done this a million times. So hopefully it's quick and easy, and it's not supposed to be complicated when we're getting started today. But 2x plus 3x is, everybody? 5x. Thank you, the one person that chimed in. All right, because I'm counting x as 2 plus 3. All right. Here I have 4 x squareds, and I'm taking away 7 x squareds for a grand total of -3 x squareds. All right, and then this is the same idea, although we maybe not have seen it as much with the square roots. I have 4 square roots of 7, and I'm taking away 7 square roots of 7, and it would be -3 square roots of 7. Again, we're just looking at basically identically looking things, and we're counting as we add and subtract and simplify. We get a little bit more complicated, we go to this. I have a 3 square root of 2 minus 3. Are they counting the exact same things? No, they are not. Since they are not, then this is fully simplified. There's nothing else I can do. 3 square root of 2 minus 3 is just going to be 3 square root of 2 minus 3. All right? And then down below, I have the 5th root of 7 and the 3rd root of 7. And so because we did this just in the last lesson, we're going to make that and do our roots as exponents. I'm going to rewrite it as negative. Use blue here. Negative. And it will be 7 to the 1/5 power. All right. The 5th root is the 1/5 power. And then I'll have plus 7 to the 1/3 power. And now we have something that looks like things we've done in the past. Are they the same base? Yes. Now, if you remember in the past, when I had things that were same bases and multiplied, like if I had a to the, I'm not going to do b, a to the 5th times a to the 3rd, we said, well, that's 8, a to the 8th. because I have same bases, so then we add exponents. In this case, though, I am adding them, not multiplying. So in a lot of ways, the most common mistake I will see people make is they will try to combine these two, and we actually cannot. Since they are not multiplying, it's adding, unless they are identical roots, like we had on the last slide, root 7 and root 7, this is the third root of 7, this is the fifth root of 7. Since they're not the exact same root, I cannot combine them, and I can find that this actually is also already completely simplified. Okay, so one example that you can look at, if you go with the square root of 9 plus the square root of 9 on the left side, so the square root, that's 3 plus 3, and that's equal to 6. On the right side, if I did the square root of 9 plus 9, that would be the square root of 18, which is not 6. All right. If we do the same thing in the bottom, and I do the square root of 9 times the square root of 9, so this over here would be 3 times 3, which is 9. On the right side, if I had the square root of 9 times 9, that's the square root of 81, and that is 9. So I have one example that does work for the bottom, but obviously does not work for the top. So at this point, we've proven that this one up here is false. We've shown one counterexample for how we know that it's false, because 6 does not equal the square root of 18. Down here, we have one example that is working, but that doesn't mean that it works for all numbers. So then I have to think beyond sometimes the numbers, if I can't come up with one, to some of the reasons and rationales, maybe some of the principles and properties that we've learned in this class already. So if I rewrite this as a to the 1/2 times b to the 1/2, and then working backwards, that would be the same as a, if I have something raised to a power and it's only multiplying, the reverse property of powers raised to powers is drawing it out. If I have two things that have the same power and I'm multiplying, I can essentially pull that power out and write it like this, which is the same as the square root of AB. So in this case, this one is true. Oh, I can't even spell. True. The top one was false. And again, we get back to some things that we've talked about. Exponents are the same as multiplying. So if I'm multiplying things, I can oftentimes use my properties of exponents when I'm multiplying to manipulate one side to the other side. What I cannot do when I'm adding and subtracting is combine those in any way, because exponents and roots are related, but the adding is not an exponent. Adding is just adding and subtracting their inverse operations. All right, so down here we can go from this. Now, if you're looking at this and can't remember what's going on there, the property that we had was, choose a different color here. If I have a to the third b squared, and I take that to the giant power of 4, the property we've talked about in the past is I can, because I'm really doing it times itself 4 times. So it'd be a to the third times a to the third times a to the third times a to the third, which is a to the 12th. So when I have powers raised to higher powers, they multiply. And then if I had multiplied this whole thing out and shown like the giant steps, it would be a third b squared times a third b squared times a third b squared times a third b squared. So I'd have b squared 4 times, or b to the 8th power. What I did over here is I did it reverse. I assumed that they both had been multiplied by a half. So the idea is I'm dividing that 1/2 out instead of multiplying. So now it's a to the first, b to the first. If I were to take this and simplify it like we did over here, this would simplify into this step, which is what we started with. So sometimes in our processes of defining or proving things, we're actually not simplifying. We're going to do the opposite of simplifying to work ourselves backwards into what our original statement was, which is this equal to that? And the answer is yes, that's true. So as we're looking at this, again, looking at those cubes that I know cubes of, and then thinking, is there a number there that I know goes into either 48 or goes into 6? 6 is easy. The only thing here that goes into 6 is 1, and that's pretty, I don't know, it's not a very exciting thing to divide by because you just end up with the same thing. So the right one is easier to simplify quicker because the cube root of 6 will just be the cube root of 6. All right, but then because roots are the same as exponents, and since exponents can be split up when multiplying, so can roots. So this would also be the cube root of y to the 4th. And the reason I do that, make sure you keep your, by the way, see how I extended that beyond? Make sure you keep that 4th under the square root because it's under the square root here. I see this happen time and time again. You don't extend your square roots or your cube roots or whatever roots, and the next thing you know, you can't remember if that 4th was outside or the 4th was inside because it's a big difference. All right, but then what I'm going to do is I'm going to leave this as the cube root of 6, and then I'm going to multiplying and change that cube root to an exponent. So I'm going to have y to the 4th to the 1/3. And the reason I do that is because then this would be y to the 4/3. And I notice that it's over 1. Anytime that it's over 1, that would be the same as having y to the 3/3. And 3/3 is 1. So I'm going to just have y to the 1. I'll write 3/3 here, but in a second I'm going to erase it. And then y to the 1/3. All right, if I have y to the 3/3, that's just y to the 1 power. That simplifies into y times, and then I'm going to go back to cube root of just 1y. How did I do that? The 3 in the denominator means it's a cube root. The 1 means there's 1 in there. Up here we had 4 of them in the cube root, which is what we had up here at the top. 4 of the y's inside the cube root. So as that fraction looks, the numerator tells me how many I started with on the y. The denominator tells me the root level. Cube root, y to the 4th. That's what I had, cube root of y to the 4th, here to here. Now, if you do this a lot, you'll start getting to this place and go, wait, here's 4. It's the cube root. So that means 3 of these come out to make 1 in front, which is the 1 in front down here. So 3 of the y's come out in front because it's a cube root to make 1 y out in front. And after I take 3 of them out, I'm left with 1 inside the cube root. So this last term ends up being, I have a y, this one right here. The only thing that came out of the cube root was the y. So I'm going to have a y right there. Y times the cube root of, I still have the 6 under the cube root, and I have one of the y's under the cube root. Plus, 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 all the way down. This here is more like a sub-step. So I'm not going to put a plus there. It's like a sub-step just explaining where that number came from, or that part of the term. All right, now the other one. So I'm going to slide it this way. Let's work over here for a bit. I'm thinking I'm going to take the cube root of 48 over there. And then I notice that the other one is the cube root of y to the 4th, which I already did once, so I know down here it's going to be like just this part here. I have the cube root of y to the 4th, which I already did, and I know is going to be y times the cube root of y. It's the same thing as what I had over on this side. Got to that point on that far side over here, so it's going to come down and be the same thing. But here I've got cube root of 48. Is there a number over there on the right-hand side that goes into 48 that's a cube root? And the answer is yes. 48 is divisible by 8. So I can rewrite 48 as the cube root of 8 times the cube root of 6. Because if I was going to simplify that, going back to that last slide we did, the square root of a times the square root of b is the square root of ab. And then if we go reverse, The cube root of 48 is equal to the cube root of 8 times the cube root of 6, because 6 times 8 is 48. And then, fancy this, I know the cube root of 8. And that's why we're doing this. I want to find numbers that I know the cube roots of. The cube root of 8 is 2, because 2 cubed is 8, times the cube root of 6. Then I look at the cube root of 6. Is there a number, again, this is the processes we're thinking through, is there a number that goes into 6 that I know the cube root of? And I go over here to my list. 125, 64, 27, 8, 1. 1 is the only one, but really if I do that, then I'll have 1 times the cube root of 6. I'm left with the same exact thing, which doesn't simplify anything else for me. So at this point, I am done with the cube root of 48. So bringing that one down, out in front, I'm going to have 2 times the cube root of 6 times y times the cube root of y. I have 2 things in cube roots. They can combine into the cube root of 6y. And then out in front, I have 2y. Again, the 2 and the y are not inside of the cube roots, so they can multiply to 2y. The 2 things inside the cube roots multiply, cube root of 6y. And now look at this. Again, where we started today, I think of this as almost like an x or a variable. As long as it's identical, cube root of 6y, cube root of 6y, I'm counting them. I have y, cube roots of 6y, and I have 2y, cube roots of 6y, for a grand total of 3y, cube root of 6y. And that would be where we started with and how we got to a final solution of simplifying. Lots of things to keep track of as you're going through here, but it's much like we've done with factoring. That's the first thing we're going to look to do. Can I factor things out to a place where I can then say, I can see commonalities, and then I can add and subtract commonalities, or in some cases, factor out commonalities. So in this case here, simplify again is the instructions for this. It's already been factored. So, I mean, typically our one of 2 ways of going most of the problems we're going to do in this course is we're either going to be factoring something or going to be simplifying something because they are reverse practices. So in this case, I've got 2 sets of parentheses. I got a binomial in each. Binomial means 2 terms. Binomial. So then I'm thinking about multiplying. And whether or not you've done FOIL or you do it some other way, I mean, the old school way of multiplying also works. I can take this and put it underneath and go root 2x plus 5, and then I can multiply. Remember doing this? 5 times negative 5 is negative 25. 5 times square root of 2x is 5 square root of 2x. Bring down a 0. Then I go this times that, so 2x, square root of 2x times negative 5 is negative 5 square root of 2x. And by the way, it's a plus 0. It can be a minus 0. It doesn't really matter. Can't subtract 0 and add 0 and get a different number. All right, and then square root of 2x times square root of 2x. So it's square root of 2x squared. And then we're going to, add these up. Negative 25. That middle term adds to 0. 5 root 2x, negative 5 root 2x. Make sure I keep those both underneath because it's all under the square root. It's the identical thing, but adding the inverse, so that adds to 0. And then I have something square rooted that's then squared. Something square rooted that's squared is the same. Again, they're inverse operations, so I'm left with 2x. So my final answer would be 2x minus 25. All right. Now, some of you may have done this. FOIL. That's the same. I mean, that's really what I did when I did long multiplication. It's just sometimes, well, in this case, it's easier probably just to do FOIL. But long multiplication comes in handy occasionally when you have really long polynomials and you want to keep track of everything and all the rows and columns. And then you can see what because if you set them up the exact same way, then these columns will stay lined up so you know which ones add together. But either way. All right, now, This looks like what we've done with difference of squares. The only difference is my final solution, this is a square, this is not. All right, so if I were going to tell you to factor this as if it were a difference of squares, you would say, well, what times itself is 2x? There isn't an easy thing, so it's the square root of 2x times the square root of 2x. All right. It's unlikely I would ever ask you to do that, but that's where that's coming from. But again, another example of what a difference of squares multiplies out to, because, you know, it's an important topic that I've said like 15, 20 times now. Moving on, now we've got this. Most common mistake people are going to make is they're going to bring the square in, and you can't do that because there's adding. There's adding in here, which means I have to think of it as squaring. What does squaring mean? It means x plus 1 under the square root plus 5 times x plus 1 plus 5. Squaring means times itself. And then I'll go ahead and I'll FOIL this one out. Firsts, square root of x plus 1 times the square root of x plus 1 is the square root of x plus 1 squared. Outsides, 5 times root x plus 1. Insides, 5 times root x plus 1. Lasts, 25. Something square rooted that then is squared. The squaring and square rooted are inverse operations. I'm left with x plus 1 plus these together give me 10 square roots of x plus 1. And then I have plus 25. And in most cases, when we'd FOIL, in that case, we'd be done. But then we've gotten something out of the square root. So they can add this 1 and the 25. So I end up with x plus 10 root x plus 1 plus 26. More simplifying. Or I'm going to at least attempt to see if I can simplify. So on the left-hand side, when I have something like this, I'll usually split it up. Again, multiplying and dividing, I can split up underneath the square roots. So I have square root of 11 over the square root of 8. And then over here I have the cube root of 11 over 6. Do those have the same denominator? No. Is the square root of 8 somehow connected to 6? No. Can I combine these into one fraction? Yes, and let's see how we do that. I'm going to start by taking the square root of 8, and I'm going to put it into simplified radical form. Simplified radical form means I want to find a number that goes into 8 that I know the square roots of, like we did with the cubes, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. You're thinking about all those numbers that you know the squares of. And I go, the square root of 8 can be rewritten as the square root of 4 times the square root of 2. Why did I choose 4 and 2? Because I know the square root of 4. Only pick a number, one of the numbers that you know the square roots of. The square root of 4 is 2. And the square root of 2 I don't know without typing it into my calculator. So the square root of 8 is rewritten as 2 square root of 2. So now I have square root of 11 over 2 times the square root of 2 minus cube root of 11 over 6. Not an easy one, but what's my common denominator? Well, my common denominator will have a 6 in it because both 2 goes into 6 and 6 goes into 6. But how do I get my 2 to a 6? I'm going to have to multiply this left one by 3 over 3. Then I also need a square root of 2 in the denominator because one of them has a square root of 2. This one already has a 6. All this one needs over here is a root 2, so I'm going to multiply this one by 1, which is the square root of 2 over 2. Again, when I'm multiplying by 1, I've said this before, I'll say it again, I'm not changing the number, just how it looks. So now, this left fraction, I'll have 6 root 2. The right fraction, I'll have 6 root 2. In the numerator, I'll have 3 times root 11. Minus, up here I'll have cube root of 11 times the square root of 2 3 root 11. That makes it look like a cube root. 3 out in front, 3 times root 11, minus, when you have multiple roots, it's common to write them in descending order. And then our instinct would be, is there a way to find a way to, because I'm multiplying, are they the same roots? No. This one's square root, that one's cube root. Okay, well, if they're not the same roots, are they at least the same bases? Nope, this one's 2 and that one's 11. So this actually would be the completely, well, there's one more step, which we're going to do in a second. But this would be the simplified form of this. Now let me check my next slide. But there's one problem that we have with this, and that will be what's called, the denominator is not rational. A rational number is a number that can be expressed as a fraction. The square root of 2 cannot be expressed as a fraction, so the denominator here would be referred to as irrational because it's an irrational number. Remember back when we talked about natural numbers and real numbers and integers? Rational and irrational are also in that conversation. A rational number is any number that can be written as a fraction. Irrational are numbers that you cannot write as a fraction. Square root of 2, it's a non-repeating decimal. It's out of your calculator. That's the only way to find it. It's irrational, which means our next step is how do we rationalize the denominator? So to rationalize the denominator basically means I have to get my roots out of my denominator, which is, we've kind of been walking down this path. How do I get rid of the square root of 2? I'm going to, without changing the number, again, I'm not going to change the number, which means I'm going to multiply it by 1. And I have to think, what can I multiply the denominator by that gets rid of the square root of 2? Well, if I multiply the denominator by the square root of 2, because those are inverse operations, and whatever I do to the bottom, I do to the top, because I'm multiplying by 1, in the bottom, the square root of 2 times the square root of 2 is the square root of 4. And the square root of 4 is 2. With square roots, this is going to be a pretty quick process. Cube roots, the next one we're going to do, a little bit more lengthy. And then in the numerator, am I square rooting both of those things? Yes. Since it's the same root and I'm multiplying, they can combine into the square root of 6. Now, if you would go back and you would type this into your calculator, and then if you type this into your calculator, and don't round anything, you're going to get identical answers. This has what's called a rationalized denominator. The denominator is no longer a square root. We're going to be expecting that this is always how I do fractions from now on. If I ever have a square root in the denominator, I need to find a way to rationalize it. And not just any square root, cube roots, fourth roots, any root that's not an actual number. All right, so now I need to get rid of, in the next one, a cube root. Well, in a square root, we just multiply it by itself twice, or by itself once, so then I have 2 of them. In order to get rid of a cube root, I have to multiply it by itself 3 times. So now, when I multiply it by this number 1, I'm going to multiply it by the cube root of 9y squared and another cube root of 9y squared. So that way I'll have 3 of them. In the top, I'm going to have the cube root of 9y squared. I'm going to have another cube root of 9y squared. What I have in the top is identical to what's in the bottom, and it's all multiplying. So this is a really complicated and ugly way of writing the number 1. Anything divided by itself is always 1. But when I do that, I'm just changing the way this looks by multiplying it by 1. So in the denominator, the cube root of the same thing of the same thing is going to leave me in the denominator with 9y squared. The cube roots disappear. If I cube something that's cube rooted, those are inverse operations. Cubing means times itself 3 times. I'm left with only what's in the denominator. Now, in the numerator, am I cube rooting everything? Yes. Which means, since I'm multiplying, I can put everything, quote unquote, together under the cube root. So I'll have the cube root of, let's see, 2 times 9 times 9. 81 times 2 is 162. X squared y to the 4th power. X squared, there's no other x's, so it says x squared. Y squared and y squared is y to the 4th. And at that point, we are like 98% of the way there. The last thing to do is look inside. Is there, no, the denominator is going to stay 9y squared. Is there anything in the numerator that I can take the cube root of? So I'm looking at the 162. Does 8 go into 162? No. How do I know that? I know, like, if you add the digits 1 plus 6 plus 2, that's 9, so definitely not going to be divisible by 8. There's another characteristic of it that goes into that. Anyways, is it divisible by 27? Maybe. So, I actually need more space than this. We'll go like that. So 162 is divisible by 27, and the answer to that is 6. So I'm going to rewrite the cube root of 162 as the cube root of 27 times the cube root of 6. And I do that because the cube root of 27 is 3, and then I'll have the cube root of 6. So in my numerator, the cube root of 162 gets rewritten as 3 times the cube root of 6. X squared will not change because it's not higher than 3. But then like we did in the previous problem, I have a y to the 4th taking the cube root. So the idea is, how many of these y's will come out and give me one y out in front? Well, if I take 3 of them out, I'll have one y out in front, leaving me only one y inside. And again, if you don't remember how we did that, go back to a previous slide or two where we did the cube root of y to the 4th. And then I look and see, oh my goodness, 3 goes into 9 3 times. Y goes into y squared once, leaving me with the final answer of the cube root of 6x squared y over 3y. So then I have this case here where my denominator has a square root, but it's not multiplying anymore. I have an adding or subtracting in the denominator, so I can't just multiply it by the square root of 3. I have to use what's called the conjugate. That's why it says using the conjugate. The conjugate is, again, we're going to be multiplying by 1, but it's going to be a fancy looking 1. And this gets back to a problem that we did a few slides ago where it was kind of like the difference of squares, where I got rid of the middle term so I didn't have any square roots left. So the conjugate is the same thing but with the different addition sign, or the different sign in the middle. Instead of subtracting, it's adding. If my original problem was adding, then I do subtracting. And whatever I have in the bottom, I have to have the exact same thing in the top because that's my fancy way of writing the number 1. So then when I multiply, in the numerator, I'm going to have just 5 times root 3 plus 2. We'll distribute in a minute. In the bottom, this is why we did another problem earlier, we're going to FOIL that. Firsts. Square root of 3 times itself is square root of 3 squared. Outsides plus 2 root 3. Insides minus 2 root 3. Lasts minus 4. In the numerator, I'll have 5 root 3 plus 10. Actually, I am going to leave it because you never know. Maybe I'll be able to reduce something. In the denominator, I have the square root of 3 times the square root of 3, which is the square root of 3 squared. Square root of 3 times square root of 3 is just 3. I have plus 2 root 3 minus 2 root 3. They add to 0. And then I have minus 4. So plus 0, minus 4. My pen is not working. There we go. So then I'll have 5 root 3 plus 2 over negative 1. 3 minus 4 is negative 1. So then final answer would be negative 5 root 3 plus 2. You could leave it like that, or you could distribute the negative 5 in. Either way, that would be a full solution and be done with that. So now we have square roots and we're going to be solving. We'll start with a couple quick ones that are relatively easier than the other ones. Whatever you do to one side of an equation, you have to do the other side of the equation. And so you say, how do I get rid of a square root? Well, if I take that and I square it and I do the same thing to the other side, square root of x squared is x. 7 squared is 49. Ta-da! That's my final answer. How do I get rid of a square root? We have to get rid of the square root before we can do anything with the 4. Roots are jail cells. Nothing inside can interact with the outside world until we get rid of the jail cell. Square it. Square it. I am left with x minus 4 equals 9. Square root, squared, those are inverse operations, so then the things inside are now freed up to interact. Add 4, x equals 13. When in doubt, when you're like, I wonder if I got the right answer, put it in here. 13 minus 4 is 9. What's the square root of 9? 3. Ta-da! It works. But then, of course, it gets more complicated because it always does. If we square both sides, I will have x minus 4 equals 9x squared. 3x times 3x, 3 times 3 is 9. X times x is x squared. Now it doesn't look quite so easy. So then what I'm going to do is I have a quadratic. It's an x squared. I want to set, anytime I have a quadratic, I want it set equal to 0. I am going to prefer to move everything to that side so that it keeps my 9 as positive. So on the left, I'll have 0 equals, and then I'll have 9x squared. I got to move the x over by subtracting x. I'm going to move the 4 over by adding 4. And now I go, oh boy, is there a way to get that factored, or do I use the quadratic formula? I tend to not like the quadratic formula because it's just a lot of work. So I'm going to see, is there a way I can do 3 and 3? Well, it can't be 2, because if I did 2's, then I'd have a 0 in the middle. If I do 1 and 4, 3 times 4 is 12, 3 times 1 is 3. That's not going to get me a negative 1. Instead of 3's, I could do a 9 and 1, but that's going to create bigger issues with 4 and 1. So I don't think there's going to be a way for me to factor it. So then I'm going to go quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. X equals a negative b. The b is negative 1 already, so now it's going to be a positive 1. Plus or minus. And it doesn't hurt somewhere to write down a equals 9. B equals negative 1. C equals 4. Just so you can keep track of what you're doing as you're running through these things. Square root of b squared, so negative 1 squared is 1, minus 4 times 9 times 4. All over 2 times 9. X equals 1 plus or minus the square root of, let's see, 4 times 9 is 36 times 4. I don't know what that is. 1 minus 144 over 18. X equals 1 plus or minus the square root of negative 143 over 18. So x equals 1 plus or minus I times the square root of 143 over 18. I is the square root of negative 1. That means I have two imaginary roots. I do not have any real numbers that make that work. So it's a good thing I couldn't factor it because they're not even going to be two real numbers. What that means if I were to actually graph this, it means I have a parabola that opens up. I know it opens up because 9 is positive. And it opens up and it never crosses the x-axis. Two imaginary roots. All right, so this, though, would be, so I get to this place and my x is going to be no real solutions. Those are my two imaginary numbers, but no real solutions. Moving on to the next one. Same idea. I'm going to square both sides. So I'm going to have x minus 4 equals, going to square that. All right, x minus 2 times x minus 2. X squared minus 4x plus 4. I'm going to move everything to the right-hand side, so it equals 0. X squared. I'm going to subtract x from both sides, so then I have negative 5x. I'm going to add 4 to both sides, so that's plus 0, which is beautiful. Because, we'll move that up. 0 equals x squared minus 5x. Can I factor? Yes. I can actually do it pretty quick because they have a GCF of x minus 5 equals 0. And now that I have it factored, I can say, what makes this 0? So I set it equal to 0. Well, when x is 0, it's 0. And 0 times anything in that, the other parenthesis will be 0. So x equals 0 is one solution. And then I'm going to set x, not equals, x minus 5 equal to 0. So when x equals 5, I put 5 in here. 5 minus 5 is 0. 0 times 5 is 0. When I put 0 in for here, 0 times negative 5, also 0. My two answers are this. And if I need to go back up, I can check. 5 minus 4 is 1. What's the square root of 1? 1. Go over here. 5 minus 2. Uh-oh, that's 3. So is that a solution? Did I do all my work right? So that's the next question. What's that?
You did minus 4 on both sides.
Oh, I should have added 4. Look at that. So I am going to have to restart this problem. Square root of x minus 4 equals x minus 2. X minus 4 equals x squared minus 4x plus 4. Add 4 to both sides. And subtract x, so 0 equals x squared minus 5x plus 8. There's a difference. All right. Do any two numbers multiply to 8 that add to 5? Nope. Then back to the quadratic formula. So using quadratic formula all the way through there, we also find we get two imaginary roots. So there are two solutions, they're just not real solutions. And you don't know that until you get to this place here with the negative. So square root of negative 7 is an imaginary number. At this point, I have no real solutions. A little bit more here now. This one's going to, I'll just get us rolling. I'm going to multiply both sides. There's a couple ways about going at this. If I move the square root of 2 over, some people like that, so I end up with the square root of 2x plus 5 over here. And then over here I'll have 3 minus the square root of 2. Because the square root of 2 is a number, right? It's not a variable, so if I move, so my variables under the exponents, or under my exponents, a root is an exponent, so it's on the left. And then I'll square both sides. So I'll have 2x plus 5 equals, and now I've got to multiply that out. So squared is the same as times itself. First 9 outsides, I'll end up with a total of negative 6 root 2's. And then last, negative times negative is positive, root 2 times root 2 is 2. So the right-hand side simplifies to 11 minus 6 the square root of 2, which again is just a number. Over here I have 2x plus 5. Subtract 5, 2x equals 6, right? Minus 5, minus 6 root 2. Divide both sides by 2. X equals 6 minus 6 root 2 all over 2. Since all my factors again are things you can add or subtract, all of them are divisible by 2. The 2 reduces here to 3 and 3. So x equals 3 minus 3 square root of 2. Ta-da. Now, if there were an x underneath that square root up here, it becomes an even more complicated problem. But recognizing that all my variables are under this one square root, like I've done before, I want to isolate that on one side all by itself, and then I can square just this to get rid of the square root to eventually solve for x. Last one, before we're going to have some time to work in class on the next set of problems. I'm going to multiply. I'm going to go, okay, what do I do to do this? If I square both sides, I get 2x equals 9. X equals 9 halves. If I plug it back in, and I go, okay, the square root of 2x is 2 times 9 halves. Is the square root of, well, see, 2 times 9 halves is the square root of 9, and the square root of 9 is 3. I'm supposed to have negative 3. What happened in this process? Well, can I ever take the square root of a number and get a negative number? No. The square root of a positive number is positive. The square root of a negative number is imaginary. I can never take the square root of a number and get a negative number. So in this, it's not a trick question, it's just trick E. Although you can find a solution, it's in what's called an extraneous solution, which means it's extra and it doesn't work. All right, and that's it for 7.4 through 7.6.